Classifying reactions, Part 2. Classification of reactions, as we discussed, is a system by which we want to organize reactions and our understanding of reactions. All chemistry wants organization, and we can classify reactions by their various characteristics. Some reactions actually have names, for instance the Grignard reaction, others do not. Even without a name, we can still classify a reaction according to its class. There are two different ways by what the atoms do, as we saw before. This considers combination and rearrangement of atoms. There are four types: combination, decomposition, single replacement or displacement, and double replacement or metathesis, and can be difficult to recognize them sometimes. We now turn to classification by type of reaction, where we're looking at the nature of the products and reactants as a whole, and there are again four classes but also a subclass. Generally, these reactions are easier to recognize. So classification by type, there are four basic types. There is a precipitation reaction, an acid neutralization, a gas evolution, and an oxidation reduction or redox reaction. The subclass of redox reaction is reaction with oxygen, which involves an actual molecular oxygen as a reactant. These reactions are based upon the identity of the substances involved. Precipitation reactions form a solid from solution, so you have to combine two aqueous solutions to form a solid. In an acid neutralization reaction, a proton, or H+, will be transferred from the acid species to a base species in reaction. In a gas evolution reaction, a gas is produced from a non-gas reactant like a liquid, a solid, or a solution. In an oxidation reduction reaction, electrons are transferred similarly to how a proton is transferred in an acid neutralization. And then a subclass of oxidation reaction, we have reaction with oxygen in which molecular oxygen or O2 gas appears in the reaction. In a precipitation reaction, we have a solid which forms from solution. A precipitation reaction will combine multiple solutions together which contain ions that are soluble, and will combine those soluble ions together in a new solution, which causes their combination to form insoluble substances. At this point, we'll have in solution a concentration of ions which is far in excess of the saturation point of the insoluble substance. This causes the reaction mixture to shift towards the solid for that insoluble substance, and we have a solid precipitation which occurs, taking those ions out of solution. The removal of those ions serves as a driving force to push the reaction forward towards completion. In a precipitation reaction, oxidation states do not change. As an example of a precipitation, sodium chloride will react with silver nitrate to produce silver chloride and sodium nitrate. The silver and the chloride combine to form an insoluble substance, which precipitates as a solid, leaving behind the residual sodium and nitrate ions, which continue as aqueous solution. Lead acetate can combine with sodium sulfide to produce lead 2 sulfide as another insoluble substance in water, and a residual sodium acetate, or 2 sodium acetates. An acid neutralization reaction occurs when we have a transfer of H+ from an acid to a base. There are various different theories which describe the behavior and action of acids, but the most prevalent is what we call Bronsted-Lowry theory, and according to this, we have protic acids which form H+ as a substance transferred from the acid to the base. So we have an H+ transferred from acid to base in an acid neutralization reaction. The base contains some sort of lone pair to accept the H+ and form a bond, and so we wind up getting a transfer of H+ from acid to base, forming a bond with the H+. Oftentimes an acid neutralization reaction will be a combination of H+ and OH- combining to form water. In these compounds, or in these reactions rather, the formation of a molecular substance is the driving force, where, for instance, water's formation is not easily reverted to H+ and OH-, and so pulls the reaction forward. An example of an acid neutralization is a reaction of HCl with sodium hydroxide. This produces sodium chloride and water. Another example is the reaction of ammonia with nitric acid. The transfer of the H+ from HNO3 to NH3 forms NH4+, leaving behind residual NO3-, which will combine with the NH4+ to make NH4NO3. A gas evolution reaction is a reaction in which we form a gas from a solid, liquid, or solution. These are classified only if there is no gas on the reactant side. The gas is produced as a product and thus is subject to a variety of different conditions to determine its solubility. Oftentimes in these gas evolution reactions, we actually have additionally either an acid-base reaction transferring a proton or an oxidation-reduction reaction transferring electrons, which occur. Usually the gases produced are of low solubility. That low solubility means that the production of the gas is once again, like a precipitation reaction, going to exceed the solubility point of the gas, causing it to then escape from solution. Some of the exceptions to this are very polar gases like HCl or NH3, which can remain in solution for appreciable quantities. The escape of the gas, though, from solution is the driving force. As the gas moves on, it is unable to revert and react backwards, thus causing the reaction to continue to move forward. If we have the presence of either H2CO3 or H2SO3 as a product in a reaction like this, H2CO3 and H2SO3 both will decompose, one forming CO2 as a gas and the other forming SO2 as a gas. So examples of gas evolution reactions: zinc can react with sulfuric acid to produce zinc sulfate and hydrogen gas. Hydrochloric acid can react with sodium bicarbonate to form sodium chloride and H2CO3 carbonic acid. The H2CO3 then decomposes to form H2O and CO2 as a gas. Oxidation-reduction reactions, or redox reactions, occur where we have a transfer of electrons from one species to another. In these kind of reactions, the oxidation states will change, unlike the acid-base and precipitation reactions that we've seen previously, or most times the gas evolution reactions. However, if gas evolution is oxidation reduction, its oxidation states will change. In an oxidation reduction reaction, at least one electron has to be transferred, but there can be more than one, depending upon the circumstances. In an oxidation reduction reaction, the transfer of electrons occurs from what we call a more active species to a less active species. So for the metals, for instance, something which is more reactive to form a cation will transfer electrons to something less reactive to form a cation. In an anion, like a halogen, something which is more likely to take electrons and form an anion is going to steal the electrons from something less likely to form an anion. Oftentimes, oxidation-reduction reactions occur as a displacement reaction, where the active element displaces the more noble element, or the less reactive element. The relative activities in oxidation-reduction reactions can be viewed and are ranked according to experimental activity series, which compare the reactivities in oxidation reduction of different metals and or halogens against each other. An example of an oxidation reduction reaction is the reaction of magnesium with silver nitrate. Reaction of magnesium with silver nitrate produces magnesium nitrate and silver as a solid. So magnesium goes from a 0 oxidation state to a 2+, where silver goes from a 1+ to a 0. In a halogen example, fluorine can react with KCl, potassium chloride. This produces potassium fluoride, where we have 2 potassium fluorides, and then chlorine gas. Note that the oxidation state of the fluorine goes from 0 to 1-, whereas the chlorine goes from 1- to 0. Reactions with oxygen are a special classification of oxidation-reduction reaction in which we have molecular oxygen, or O2 gas, involved in the reaction as a reactant. Depending on the rate the reaction occurs, these can go under different names, things like corrosion reactions or combustion reactions, etc. The transfer of electrons, which generally occurs to oxygen from another substance, where oxygen will combine with different elements in the reactant as when they form products, and so you wind up usually getting oxygen distributed through whatever the other substance it reacts with is. These can occur as reactions with either compounds or with elements. For example, a chemical reaction with this, if you combine methane, CH4, with oxygen, this reaction will produce carbon dioxide and water, so you see the oxygen combines both with the carbon and with the hydrogen to make compounds. Here we see the oxidation state of carbon at 4- becoming 4+ as a product, the oxidation state of oxygen as a neutral 0 becoming a 2- in both the carbon dioxide and the water. The hydrogen's 1+ remains a 1+ from the methane to the water. The reaction of oxygen with iron can produce iron oxide. For example, if we combine enough oxygen, we'll get iron 3 oxide. And so here we have oxygen with an oxidation state of 0, and iron with an oxidation state of 0, producing iron oxide, where iron 3 oxide here has now an oxidation state of 3+ on the iron and 2- on the oxygen.